So, the physics, chemical effects of electric current. Your elders might have cautioned you against touching an electrical appliance with wet hands. But do you know why it is dangerous to touch an electrical appliance with wet hands?
Electricity is a conductor.
Electricity,
water is a conductor.
Water is a conductor, yeah. We have learned earlier that the materials which allow electric current to pass through them are good conductors of electricity. What is a good conductor?
Materials allow electric current.
That allow electric current is a good conductor. On the other hand, materials which do not allow electric current to pass through them easily are poor conductors of electricity. This is called as poor conductors. Okay. In class, in the earlier class 6, we made a tester to test whether a particular material allows electric current to pass through it or not. Do you recall how the tester helped us in deciding that? We found that metals such as copper and aluminum conduct electricity, whereas materials such as rubber, plastic, and wood do not conduct electricity. However, so far we have used our tester to test materials which were in solid state. But what about liquids? Do liquids also conduct electricity? Okay, let us find out. By the way, Pahili and Bujho want to remind you that one should not experiment with electric supply from the mains or a generator or an inverter. Use only electric cells for all the activities suggested here. Do liquids conduct electricity? To test whether a liquid allows electric current to pass through it or not, we can use the same tester which we made in class 6. However, replace the cell on a battery also. Replace the cell by a battery. Also, before using the tester, we should check whether it is working or not. Okay? But have you done this activity? No. Do you recall the activity? No. So you have a tester, and on the one end it is wired to a battery, to the end of a battery, and then on the other end of the battery, you again connect it and take it to the bulb. Take it to a very small bulb. And then from the bulb, you connect one wire to the tester rod, the same tester rod. Okay? So now, you have a tester. Where is the one end of the tester connected to? To the one end of the battery. Okay? Battery cell. And then the other end of the battery, again one wiring to bulb. Right? And then from the bulb to? No. From the bulb to the tester. You kind of began with the tester. Tester to one end of battery and to the other end of, and then one small bulb and to the tester back. Replace the cell by a battery. So instead of now the cell, we replaced it by a battery. So now we are taking the tester. Tester has two parts. One is that iron part, and then the other is the handle part. Right? So we are connecting it to the tester iron, the metallic part. Tester has a metallic part and the handle. Right? Handle.
What's a tester?
Tester is like a screwdriver, but here you test it. You test whether current is passing through. Okay, it is like a screwdriver. You have a handle, you have a metallic part, and you insert the metallic part into the power line. Okay, and you press the button at the top. You just touch it. You do the earthing, and then the light will glow when there is power. Okay. However, replace the cell by a battery. Also, before using the tester, we should check whether it is working or not. Now activity. So what is the first activity? Join the free ends of the tester together for a moment. This completes the circuit of the tester and the bulb should glow. However, if the bulb does not glow, it means that the tester is not working. Can you think of the possible reasons? Is it possible that the connections are loose,
The bulb could
or
be
the bulb
fused.
is fused, or your cells are used up? Check that all the connections are tight. If they are, then replace the bulb with another bulb. Now test if the tester is working or not. If it is still not working, then replace the cells with fresh cells. So now we made sure that the tester is working. Now our tester is working. Let us use it to test the various liquids. Again, now there is another caution Pahili and Buju wants to share with you. While checking your tester, do not join its free ends for more than a few seconds. Otherwise, the cells of the battery will drain very quickly. Okay, just for a few seconds. So we are just doing an experiment. Otherwise, the cells will drain very quickly. Now, the next activity is collect a few small plastic or rubber caps of discarded bottles and clean them. Discarded bottles. Pour 1 teaspoon of lemon juice or vinegar in one cap. Bring your tester over this cap and let the ends of the tester dip into lemon juice or vinegar as shown in figure 14.2. So ends of the tester is you are just dipping it into the vinegar. Take care that the ends are not more than 1 centimeter apart, but at the same time do not touch each other. So the end of the ends, right? Let the ends of the tester dip into the lemon juice. At the same time, not touch each other. Does the bulb of the tester glow? Does lemon juice or vinegar conduct electricity? How would you classify lemon juice or vinegar? A good conductor or a poor conductor. So now by doing the test, you will see whether the bulb is glowing brightly, right? So now that's what we are seeing. When the liquid between the two ends of the tester allows electric current to pass the circuit Okay, when the liquid between the two ends of the tester allows the electric current to pass, the circuit of the tester becomes complete. The current flows in the circuit and the bulb glows. When the liquid does not allow the electric current to pass, the circuit of the tester is not complete and the bulb does not glow. In some situations, even though the liquid is conducting, the bulb may not glow. It may have happened in activity 14.2, that is the previous activity, what we just did. What can be the reason?
Bulb could be fused.
Do you remember why the bulb glows? When the electric current passes through it, due to the heating effect of current,
The fuse heat
the
of
filament of the bulb gets heated to a high temperature and it starts glowing. However, if the current through a circuit is too weak, the filament does not get heated sufficiently and it does not glow. And why is the current in the circuit weak? Well, though a material may conduct electricity, it may not conduct it as easily as a metal. As a result, the circuit of the tester may be complete and yet the current through it may be too weak to make the bulb glow. Can we make another tester which can detect a weak current? You may use an LED in place of electric bulb in the tester of figure 14.2. LED. So this is the LED, right? LED glows even when a weak electric current flows through it. You see, this is LED picture. Yeah? So LED glows even when a weak electric current flows through it. There are two wires called leads attached to an LED. One lead is slightly longer than the other. Remember that while connecting to a circuit. What do you have to remember?
A lead has ends.
Two wires called
Wires
leads.
called leads.
Hmm.
One lead is
Longer than the other. Okay. So the longer lead is always connected to the positive terminal of the battery. And the shorter lead is connected to the negative terminal of the battery. Okay, but remember this. Longer is positive, smaller is negative. So can we make another tester which can detect a weak current? So now this is what. We can use another effect of an electric current to make another kind of tester. Do you recall that electric current produces a magnetic effect? Do you recall? Alright. What happens to a compass needle kept nearby when current flows in a wire?
Gets deflected.
Even if the current is small, the deflection of the magnetic needle can be seen. Can we make a tester using the magnetic effect of currents? Let's find out. Take the tray from inside a discarded matchbox. What is it?
Take the tray from
Take the tray from inside a discarded matchbox. Wrap an electric wire a few times around the tray. So basically you're taking the matchbox as a tray. Okay. Take the tray from inside the discarded matchbox. Like matchbox has one tray inside, right? Made of that box. That's the one. Wrap an electric wire a few times around the tray. Place a small compass needle inside the tray. Now connect one free end of the wire to the terminal of a battery. Leave the other end free. Take another piece of wire and connect it to the other terminal of the battery. Join the free ends of the two wires momentarily. The compass needle would show deflection. Your tester with two free ends of the wire is ready. You see? Your tester with two free ends of the wire is ready. Now repeat activity 14.2, which is the previous activity. What is the previous activity? Connecting to the end of a bulb. Yeah? So now we got a tester here. Right? What does this tester now contain? It has two ends of wire and the wire is wrapped around the tray of the box. Right? And then within that box is your compass. What compass?
the compass with a magnetic needle.
Magnetic needle compass. Yeah, okay. Do you find a deflection in the compass needle the moment you dip the free ends of the tester in lemon juice? Take out the ends of the tester from the lemon juice. Dip them in water and then wipe them dry. Repeat the activity with other liquids such as tap water, vegetable oil, milk, honey. And you got to remember to wash and wipe dry the ends of tester after testing each liquid. In each case, observe whether the magnetic needle shows deflection or not. Record your observations in table 4.1. So you have a table of material, compass needle shows deflection, yes or no, and it's whether it's a good conductor or poor conductor. Okay. From table 4.1, we find that some liquids are good conductors of electricity and some are poor conductors. Now, again, Pahali and Bojho comes and tells you a tip. When the free ends of the tester do not touch each other, there is an air gap between them. Pahali knows that air is a poor conductor of electricity. Do you know? Air is a poor conductor of electricity. But do you know it is a blessing? Why it is a blessing?
Because otherwise,
Otherwise, you can't live. Right? The moment we have a power line there, that's it. Now, if air is a conductor, then that's it. Like, you'll all be roasted. Okay. Pagli knows that air is a poor conductor of electricity, but he has also read that during lightning, an electric current passes through air. She wonders if air is indeed a poor conductor under all conditions. And this makes Bojho, not only Bojho, even me, ask whether other materials classified as poor conductors also allow electricity to pass under certain conditions. Brilliant question, no? Air is a poor conductor, but how is lightning? coming across.
Lightning is actually caused due to the accumulation of charged particles in the cloud. So when these
No, the question,
particles accumulate
the curiosity question is, we looked at air as a poor conductor. So the curiosity question is, then how come lightning, we hear that lightning electric current passes through air? How? Logical question, right? So which means, other materials classified as poor conductors also allow electricity to pass under certain conditions. So, actually under certain conditions, most materials can conduct. You see, here is the difference. That is why it is preferable to classify materials as good conductors and poor conductors instead of classifying as conductors and insulators. Remember, you immediately said insulator, right? But rather than that, good conductor, poor conductor. Only the conditions. When you vary the conditions. There are some conditions which you can vary. Not only we, when nature varies. So in a different conditions, we see that some are poor conductor and some are good conductor. We have tested the conduction of electricity through tap water. Let's now test the conduction of electricity through distilled water. What is distilled water, by the way?
Water that is purified through chemical process.
Come on. The simple distillation. What is simple distillation? Why are you thinking of chemical process? Simple. Yeah, just boil, vapor, collect vapor and condense. That's a distilled water. Yeah. Oh, okay.
Those chemical processes.
Okay, so that's a different one, right? So that is purification, and it can also be done through chemical processing. But the simple distillation is take water, boil it, then vapor, collect vapors, condense it, then you get. Why do we do this? What's the use of this?
To kill the bacteria.
Kill the bacteria, germs, one thing, and also now you are collecting from vapor. So the germs, bacteria, virus don't become vapor. Okay, so that's the brilliance of that process. So you collect vapors, then you condense it. So now this is pure water. Okay. So now, next activity. Take about two spoonfuls of distilled water in a clean and dry plastic or rubber cap of a bottle. What is it? 2 teaspoonfuls of distilled water in a clean and dry plastic or rubber cap of a bottle. You may obtain distilled water from your school science lab. You may also get distilled water from a medical store or a doctor or a nurse. Use a tester to test whether distilled water conducts electricity or not. What do you find? Does distilled water conduct electricity?
No.
Now dissolve a pinch of common salt in distilled water. Again test. What do you conclude this time? When salt is dissolved in distilled water, we obtain salt solution. This is a conductor of electricity. The water that we get from sources such as taps, hand pumps, wells, and ponds is not pure. It may contain several salts dissolved in it. Small amounts of mineral salts are naturally present in it. This water is thus a good conductor of electricity. On the other hand, distilled water is free of salts and is a poor conductor. How is distilled water free of salts?
Because the salt doesn't become vapor.
The salt doesn't become vapor, yeah. You're just taking the form. You're taking the water to a different form, and yeah. Small amounts of mineral salts present naturally in water are beneficial for human health. However, these salts make water a good conductor, so we should never handle electrical appliances with wet hands or while standing on a wet floor. We have found that common salt, when dissolved in distilled water, makes it a good conductor. What are the other substances which, when dissolved in distilled water, make it conducting? Let us find out. So now we do the next activity. Take three clean plastic or rubber caps of bottles. What is it?
Take three clean rubber
Clean plastic, rubber caps, bottles. By the way, why are they talking about clean?
Because you don't want the
Hold on. Three. Okay, so you are on air. Plastic caps or bottles. Pour about 2 teaspoonfuls of distilled water in each of them. What do you have to do?
or 2 or 3
2 teaspoonfuls of distilled water in each of them. In each of what?
the caps, rubber or plastic.
Rubber or plastic caps. What does it have?
Water,
Distilled water, yeah. Add a few drops of lemon juice or dilute hydrochloric acid to distilled water in one cap. Now in the second cap, so what did you add in the first cap?
dilute hydrochloric acid.
Dilute hydrochloric or lemon juice. Few drops. By the way, why dilute hydrochloric acid?
It's a good point.
No. If you put concentrated, it will immediately burst. It's a very highly reactive acid.
With water,
It will start reacting immediately. You may get hurt. We are doing a small experiment, right? It is like, have you seen water into the boiling oil? So that kind of experience you will see.
water
That's a
in
different.
boiling oil.
Sorry, yeah. See, when you put so there is a hot oil and then you put onions or you put mustard and then kind of breaks, right? So it's a different process, but that's kind of similar here. So hydrochloric acid immediately starts reacting with the water H2O molecules.
But dilute hydrochloric acid is that.
So that is why we add dilute hydrochloric acid, okay? I'm just emphasizing that here. To distilled water in one cap. Now in the second cap containing distilled water, add a few drops of a base such as caustic soda or potassium iodide. Add a little sugar to the distilled water in the third cap and dissolve it. So now what all these three caps, what did we do?
Dilute
In the first cap, what did we add?
dilute hydrochloric acid
Or lemon juice. Okay, second,
base,
A base.
solution like caustic.
a base like caustic or potassium iodide. And the third,
Third one, salt.
sugar. Alright, we bring in sugar. Test which solutions conduct electricity and which do not. What results do you obtain? Alright, most liquids that conduct electricity are solutions of acids, bases, and salts. When an electric current flows through a conducting solution, does it produce an effect on the solution? When an electric current flows through a conducting solution, does it produce an effect on the solution? Now that is what we are going to look. So far, what did we see in this section? We just looked at, do liquids conduct electricity? That is what we explored. We began the session with, and we did some experiments. And what did we now find so far? See, we began the section with, do liquids conduct electricity? And then we did some series of experiments. And what do we conclude now?
What effects occur on the liquid?
No, in the first section, right? So far in the section, we began the section with, do liquids conduct electricity? And we did the experiments to find out what?
To find out whether they conduct.
And what is the conclusion? What did we conclude?
Certainly.
Yes, liquids conduct electricity. That's the first conclusion. Always first start with the base, with the simple. Yes, liquids conduct electricity. And what more did we see? Some are poor conductors, some are good conductors. What else did we see?
We saw distilled water.
You saw distilled water, yeah, that you saw. But with respect to this concept, what we are trying to learn, what did we see? We saw distilled water is a poor conductor or good conductor. Why? Why it is a poor conductor?
Because it is free of salt.
Distilled water is free of salt, so it's poor conductor. So far, what we have seen is most liquids conduct electricity, and their solutions of acids, bases, and salts. Yeah. Now we are now going to look at when current flows. Now, does it produce effect on the solution? Right. So far we saw yes, it's conducting. Now we are going to look at okay, all right. Now we liquids conduct, but now okay, what does it? What is the effect? What is the effect of it? And that brings us to the section chemical effects of electric current. So in the previous class, class 7, we have learned some effects of electric current. Can you list the effects? What effect does the current produce when it flows through a conducting solution?
Magnetic
Let us
effect,
find out.
heating.
Okay, let's find out. Okay, what are the effects of electric current?
Magnetic effect,
Magnetic effect,
heating effect,
heating effect,
light energy.
yeah, light energy, but then it is a heating effect, right? So the heating effect, superheated, then it reacts and then it produces light. Okay. All right. So now here is another activity. Take out carbon rods carefully from two discarded cells. Carbon rods carefully from two discarded cells. Clean their metal caps with sandpaper. Metal caps with sandpaper. Why sandpaper?
Sandpaper makes the area smooth and takes away dust particles.
Take away the dust particles and rust particles. Okay, so you're kind of cleaning. Sandpaper. Wrap copper wires around the metal caps of the carbon rods and join them to a battery. Okay. Wrap copper wires around the metal caps of the carbon rod, join them to a battery. We call this two electrodes. Look at this picture. So what do you see in this picture?
Two electrodes.
Huh?
Two electrodes.
Okay. So in this picture, now what are those two? Where are the carbon rods? So here are the carbon rods. Okay. And here is that circuit, right? That thing goes. You see? That line, that wire goes. Yeah? Alright. Metal cap, carbon rod, and then what? Then water. Passing through water. Clean their metal caps. Okay, we saw that. Join them to a battery. We call this two rods, electrodes. Instead of carbon rods, you may take two iron nails about 6 centimeters long. Instead of carbon rods, you can also take iron. Pour a cupful of water in a glass plastic bowl. What are you doing now? What did you just do? What did you just do? No, you're listening to me. Like, what did you just do?
Yeah, we poured some.
We poured a cupful of water in a glass plastic bowl. Which bowl?
Plastic.
Glass or plastic. What did we pour into it?
Water. Four or five cups.
Cupful. Alright. Add a teaspoon of salt or a few drops of lemon juice to water to make it more conducting. Now immerse the electrodes in the solution. Make sure that the metal caps of the carbon rods are outside the water. Make sure
The
metal caps of carbon rods are outside the water. Wait for 3 to 4 minutes. Observe the electrodes carefully. Do you notice any gas bubbles near the electrodes? So you'll be noticing gas bubbles. Can we call the change taking place in the solution a chemical change? Recall the definition of chemical change that you learnt in class 7.
A gas is evolved in a chemical reaction.
No, definition of a chemical change.
A reaction that takes place
Takes place
And wait,
Definition
the
of
occurrence
chemical
of a
change.
change in the chemical properties of
Occurrence of a change in chemical properties
materials
in a material is called
chemical reaction.
chemical change. Right? That's a chemical reaction. That's how we say it is a chemical reaction. What is it again?
The occurrence of a change
Occurrence
in the
of a
chemical
change in the
properties of
chemical properties. All right. Okay. So now we'll just took a brief history. So recall the definition of a chemical change. Okay. So in 1800, so here is an interesting tidbit. In 1800 is the start of what century?
1800
Hmm.
the 17th century. Sorry, the 19th
Come on,
century.
yeah, 19th century. So 1800 is start of 19th century. It's often confusion to many. That's why I asked you. So a British chemist, William Nicholson, who?
William Nicholson.
Yeah, he was born in 1753 to 1815. He died, I think, in 1753 to 1815. He lived. So how old is he?
1815 or 62.
1753 to 1815. How old is he?
Yes, only 62.
62. All right. Had shown that if electrodes were immersed in water and a current was passed, bubbles of oxygen and hydrogen were produced. What bubbles?
Bubbles of oxygen and hydrogen.
All right. Oxygen bubbles formed on the electrode connected to the positive terminal of the battery, and hydrogen bubbles formed on the other electrode. Can you think of an application for this?
Electrodes.
Oxygen bubbles formed on the electrode connected to the positive terminal of the battery, and hydrogen bubbles formed on the other electrode. Can you think of an application?
Can be used to generate electricity.
No, but how? No.
Biogas.
No, think. What bubbles are you generating?
Oxygen.
What's the
breaking
application of this? What's the application of this? What he found?
You can break up water to make oxygen.
Had shown that if electrodes are immersed in water and a current was passed, bubbles of oxygen and hydrogen were produced. So you are producing oxygen. So how do you apply? Where do you apply this? If you are there,
Global warming.
think. No, where do you apply? Apply means putting it to use. You are producing by passing current through electrodes. Now, through water, you are producing. You are breaking it, and you are producing oxygen. Now you're generating oxygen. Where will you now apply?
Generating oxygen.
Come on. Where will you use oxygen? You will use oxygen to breathe. So now where will you apply?
The atmosphere.
No, to breathe. Moment you kind of now produce oxygen. So now you will produce it to the places where there is no oxygen. And where the places where you want to go and explore. Right? There are some places there is no oxygen. So what do you do? For deep sea diving, do you see some cylinders people will be on their back?
Yeah. That's oxygen that got trapped from the atmosphere.
Yeah. Like after that, later to that, we also produced it and then you put it into compressed. But now these are all the applications. So now we are now able to generate oxygen. Right? From what?
From what?
Water. Right? And then you generate the oxygen, then you compress it. Correct? Into those vessels. And you also see in the hospital they keep in the incubator, what do they keep? Oxygen cylinders or oxygen pipes. Have you heard of the recent accident in one hospital in Chennai, where due to great rain and the floods, their oxygen pipes got cut, so they were not able to continue feeding oxygen to some patients, and many patients died. Have you heard of that news? It happened less than a year back. No? Okay. All right. So, who founded this? Who discovered this?
That guy was born.
What is the name? William Nicholson, a British chemist. So the passage of an electric current through a conducting solution causes chemical reactions. As a result, bubbles of a gas may be formed on the electrodes. Bubbles of a gas may be formed on the electrodes. Deposits of metal may be seen on electrodes. What do you see after the experimentation? Deposits of metal. Changes of color of solution may occur. So now by the way, we are looking at the effects. Effects of what? Electrolysis. Electric current flowing through the solution. Yeah. Bubbles of a gas may be formed on the electrodes. Deposits of metal may be seen on electrodes. Changes of color of solutions may occur. The reaction would depend on what solution and electrodes are used. And the reactions may depend on solution electrodes are used. These are some of the chemical effects of the electric current. So what are the effects of the electric current? What are the effects? What?
Gas bubbles near the electrodes.
Gas bubbles near electrodes formed on the electrodes. Then metal deposits on the electrodes. Then
Magnetic current.
what are the properties here? Simple. There is an electrode, there is a solution, and electricity is passing. So color of solutions, change of color of solutions, right? Just think of, okay, there is this electrode, there is a solution, and it is touching, and now electricity is passing through it. Now you just only have to think of, okay, what changes happen on the electrodes? Some metal deposits, and then what other you observe near the electrodes? Gas bubbles, right? And then to the solution, what change happened to the solution?
Changes in color.
Changes in color. All right. The reaction will depend on what solution electrodes are used. These are some of the chemical effects of the electric current. All right. Now coming back to Bojo. Let's say Bojo decided to test whether some fruits and vegetables also conduct electricity or not. Okay. Fruits and vegetables also conduct electricity or not. He cut a potato into two halves and inserted the copper wires of a tester into it. Just then his mother called him and he forgot to take out the wires of the tester inserted into the potato. When he came back after half an hour, he noticed that there was a greenish blue spot on the potato around one wire, whereas there was no such spot around the other wire. Okay, so look here. So now, what is this?
A greenish blue spot.
Huh?
Greenish blue spot on the.
What do you see in the picture? Potato, wire.
Yeah.
The same experiment around your matchbox, right? Mm-hmm. So you have inside of that matchbox tray and then wire going around it, one end of the wire and one potato, and then the other end yeah, and you're passing electricity into it, right? He cut a potato into two halves, and this is a battery, right? So in the picture, this is the battery, right? Okay, there was a greenish blue spot on the potato around one wire, whereas there was no such spot around other wire. He was surprised with this observation and along with Pahili repeated this activity many times. They found that it was always a wire connected to the positive terminal, which had a greenish blue spot around it. So which terminal had the greenish spot? Positive terminal. Okay. Could be used for identifying the positive terminal of a cell or a battery concealed in a box. So they felt that this discovery was very useful because it could be used for identifying the positive terminal of a cell or a battery. So now with this experiment, how do you identify a positive terminal of a battery?
Just keep in a potato.
Keep it in a potato, take a wire, take a potato and then identify it. Okay, greenish spot. They decided to report their finding to a children's magazine. Remember that Boojus set out to test whether potato conducted electricity or not. What he found was that the current produced a chemical effect in the potato. To him, this was very exciting. In fact, this is how science sometimes works. You're looking for something and you discover something else. Many important discoveries have been made in this manner. All right. So far we saw chemical effects of the electric current. So what did we see so far? So in the first section, we set out to see whether the liquids conduct electricity, and then we saw, yes, it does conduct electricity. And then we also saw the solution, like there are some properties in the solution. It is acid, bases, or the salts that is in the solution that helps in conducting electricity. And otherwise, if it's a distilled water, it doesn't conduct electricity. Okay, and then after we saw that, we also saw some solutions are poor conductors and some compositions are bad, poor conductors and good conductors. And then what did we look at? Then we looked at, okay, all right, now what's happening to the solution? Is anything happens to the solution? Right? So we saw chemical effect. And what is a chemical effect?
Like
What's a chemical, how do you define a chemical reaction?
a change,
We saw
the occurrence of a change in the chemical.
Occurrence of a change in the chemical property. Okay, so there's a chemical reaction that happens, right? And then we saw the effects of electric current through the solution, right? So we did an experiment. We took an electrodes. I mean, you can take two nails, or you can take two, and then tie each end to the wire, and then pass electric current to it. And for all these experiments, what is the source we used?
Distilled water.
No, the source of power.
Yeah,
Battery. And why did we use source of power as battery?
because
Because that is relatively safe. Okay? All right. The next is electroplating section. You know that a brand new bicycle has shiny handlebar and wheel rims. You already know, right? Our bike, the gift from Tata, had a shiny handlebar and wheel rims. However, these are accidentally scratched. The shiny coating comes off, revealing a not so shiny surface beneath. You might have also seen women using ornaments which appear to be made of gold. However, with repeated use, the gold coating wears off, revealing silver or some other metal beneath. In both these cases, a metal has a coating of another metal. Do you wonder how a layer of one metal can be deposited on top of another? Well, let's try doing it ourselves. So, we will need a copper sulfate and two copper plates of size around 10 centimeter by 4 centimeter. So, what are we taking?
copper sulfate and
Copper sulfate and two copper plates. What measurement? 10 centimeter by 4 centimeter. Yeah? And then we take 250 milliliter of distilled water in a clean and dry beaker. 250 milliliter of distilled water. Not just water, distilled water. Come on. Are you feeling sleepy? Okay. Dissolve 2 teaspoonfuls of copper sulfate in it. Add a few drops of dilute sulfuric acid to copper sulfate solution to make it more conducting. Few drops of dilute sulfuric acid. Clean copper plates with sandpaper. So again we kind of clean it. Now rinse them with water and dry them. Connect the copper plates to the terminals of a battery and immerse them in copper sulfate solution. And that brings you to this picture. Do you see the two copper plates? So So we took it, put it into like wipe it clean with water, dry it, right? And then now connect to the wires. So we made an electrode. And what does the solution contain?
Copper sulfate.
Copper sulfate. What did we take in the beaker? 250 ml of water, 250 ml of distilled water, copper sulfate, and then we also put some acid, dilute sulfuric acid, right? Okay, sulfuric or hydrochloric. What did we put? Immerse them in copper sulfate solution. Okay, dilute sulfuric acid. Allow the current to pass for about 15 minutes. Now remove the electrodes from the solution and look at them carefully. What are you looking at carefully now? Electrodes. Do you find any difference in any one of them? Do you find a coating over it? What color is the coating? Note down the terminal of the battery with which this electrode is connected. Note down what? Terminal of the battery with which this electrode is connected. After doing the after doing the electroplating activity, Pahili interchanged the electrodes and repeated the activity. What does interchanging the electrodes mean?
Replacing both of them. That is the negative terminal.
Yeah, negative terminal. Okay, just not putting the right plate to left and left to right. Right? You are now changing the connection of the wire. You are changing the positive terminal and. What do you think you should observe this time? When electric current is passed through the copper sulfate solution, copper sulfate dissociates into what? Copper and sulfate. The free copper gets drawn to the electrode. Which one gets drawn? The free copper gets drawn to the electrode. Alright. Connected to the negative terminal of the battery and gets deposited on it. Yeah? But what about the loss of copper from the solution? From the other electrode, a copper plate, an equal amount of copper gets dissolved in the solution. Interesting, right? Because these are two copper plates. A copper plate, an equal amount of copper gets dissolved in the solution. Thus, the loss of copper from the solution is restored and the process continues. This means that copper gets transferred from one electrode to the other. Copper gets transferred from one electrode to the other. Boju has an interesting tidbit. He could get only one copper plate. So he performed the activity, what we just did, by connecting a carbon rod in place of copper plate, which was connected to the negative terminal of the battery. By the way, where is this depositing happening?
On the electrode.
On which one? On the negative terminal or on the positive terminal? No, the free copper gets drawn to the electrode connected to the negative terminal of the battery and gets deposited on it. Yeah? Okay, this means that copper gets transferred from one electrode to other. Boju could get only copper plate, so he performed activity 14.7 by connecting a carbon rod in the place of copper plate, which was connected to the negative terminal of the battery. He succeeded in obtaining a coating of copper on carbon rod. So what did he do now, Boju? He substituted the negative terminal, he substituted carbon rod. So now what happened?
He got copper.
Copper, right? Where did the copper come from?
From the copper plate.
Come on.
From the copper sulfates.
Copper sulfate solution. So the copper and sulfate dissociate. So see, so far in the previous section, we saw there is a chemical reaction that happens, right? So here we are passing the current through and the copper sulfate is breaking into copper and sulfate. Correct? And the free copper is now getting deposited into the negative terminal of the electrode. And what do we have in the positive terminal? Copper. So now the solution is now deprived of copper. Now it draws from the copper. Draws from the copper electrode. Okay? Okay. He succeeded in obtaining a coating of copper on carbon rod. The process of depositing a layer of any desired metal on another material by means of electricity is called electroplating. It is one of the most common applications of chemical effects of electric current. Electroplating is a very useful process. It is widely used in industry for coating metal objects with a thin layer of a different material. The layer of metal deposited has some desired property which the metal of the object lacks. What is it? The layer of metal deposited has some desired property which the metal of the object lacks. So we began with an example. What example we began with? Jewelry. Gold coated cycle. There's a shining, but now when the cycle is injured, like it gets hurt, then you see like it is no longer shining, right? The layer of metal deposit has some desired property which the metal of the object lacks. For example, chromium plating is done on many objects such as car parts, bath taps, kitchen gas burners, bicycle and handlebars, wheel rims, and many others. What plating? What plating? Chromium plating. You got to sit straight. More recline you do, you get sleep. All right. Chromium plating is done on many objects. What are the parts we saw? Car parts, bath taps, kitchen gas burners, bicycle handlebars, wheel rims, and many others. Chromium has a what appearance? Lustrous. Okay, but what is the simple word we saw? Shiny appearance. It does not corrode. It resists scratches. However, chromium is expensive and it may not be economical to make the whole object out of chromium. So the object is made from a cheaper metal and only a coating of chromium over it is deposited. Jewelry makers electroplate silver and gold on less expensive metals. These ornaments have the appearance of silver or gold but are much less expensive. Tin cans used for storing food are made by electroplating tin onto iron. How the tin cans made? Made by electroplating tin onto iron. Tin is less reactive than iron. Thus, food does not come into contact with iron and is protected from getting spoiled. Yeah? What happens when iron, moment it comes contact with moisture, it begins rusting, right? So that is it. Now there's a tin coating. How is the coating done? Electroplating. How? You take the iron metal and then you do this process of electrolysis and then the tin comes and deposits to the iron. Thus, food does not come into contact with iron and is protected from getting spoiled. Iron is used in bridges and automobiles to provide strength. However, iron tends to corrode and rust. So, a coating of zinc is deposited on iron to protect it from corrosion and formation of rust. So, a tidbit here. In the electroplating factories, the disposal of the used conducting solution is a major concern. Now, what did we do? We are coated. We are transferred one metal layer to another metal layer. And now there is a solution. We have used a solution. What do we do with the solution? It's all changed in properties. So this is what it's talking about. The factories, the disposal of the used conducting solution is a major concern. It is a polluting waste. And there are specific disposal guidelines to protect the environment. You see? It is a polluting waste. And there are specific disposal guidelines to protect the environment. So there are some disposable guidelines which we follow. All right. So that brings us to the end of the lesson. What are the keywords we saw so far? Electrode, electroplating, Good conductor, lead, poor conductor. Yeah, LED. What you have learned? Some liquids are good conductors of electricity and some are poor conductors. Most liquids that conduct electricity are solutions of acids, bases, and salts. The passage of an electric current through a conducting liquid causes chemical reactions. What causes chemical reactions?
The process of
What?
the process of conducting electricity to a liquid.
The passage of an electric current through a conducting liquid causes chemical reactions. The resulting effects are called chemical effects of currents. Chemical effects of currents. The process of depositing a layer of any desired metal on another material by means of electricity is called electroplating. That's it. Any questions? Is this lesson clear now? Okay, now you should do the exercises by yourself. All right.